good evening. Me and my group mates were assigned to make a video about how to design a simple square isolated footing. So it's actually the very basic topic of foundation design. So yeah, I have a problem prepared right here. Here is the figure and I will read the problem. Design a square isolated footing to support a live load of 1000. By the way, these are the given. To support a live load of 1000 kilonewtons and a dead load of 700 kilonewtons. The allowable soil pressure is 200 kPa and the footing is 1.7 below NGL. So the soil density is 15 kilonewtons per cubic meter, as well as the unit weight of concrete is 24 kilonewtons per cubic meter. We are assigned to use 21 MPa for the FC prime and Fy of 360 MPa megapascals. Okay, so the column here is designed as is given as 600 by 600 600 by 600 millimeters with 822 millimeter bars as its supports right there. It's like this. Okay, so first things first, this topic is first things first, we are assigned to we need to find the equivalent soil pressure, which is named QE. Here, wait, I'll move the paper. So first things first, we need QE, which is the equivalent soil pressure, and it is equal to QA, Q allowable, minus the summation of the gamma H in the problems. So yeah, by gamma H we mean the soil here and the concrete here. Okay, so yeah, try. So this is actually, we need to try and test for something here. We need to just assume a value of H. So let's say H for concrete is 0.6 meters. Alright, here it goes. So I'll move the paper. So first things first, we need QE, which is the equivalent soil pressure, and it is equal to QA, Q allowable, minus the summation of the gamma H in the problems. So yeah, by gamma H we mean the soil here and the concrete here. Okay, so yeah, try. So this is actually, we need to try and test for something here. We need to just assume a value of H. So let's say H for concrete is 0.6 meters. Alright, here it goes. So QE is equal to 200 kPa minus gamma H of concrete, which is 0.6 times 24, along with soil minus 1.1, since 1.7 is the NGL, and then minus 0.6 is 0.1, times 15, which is the unit weight of soil. So after that, we can get the value of QE as 169.1 kPa. So after that, we have to get the dimensions of the footing itself. So there aren't any given dimensions because we are going to design for it. Say use the QE equals P over A formula. Basically QE is the equivalent solid pressure we obtained earlier with P, which is the unfactored load, actual load that is acting upon the column, which is 1000 plus 700, and the A. Since this is actually a square foot, we are asked to design a square isolated footing, so the dimensions are equal for each side. So B. So yeah, it's B squared. So basically, we are going to write the formula as 169.1 equals, 169.1 equals 1000 plus 700. It is unfactored, okay? So yeah. And over B squared, we can get the value of B as 3.17 millimeters. Yeah, that's it. E is the equivalent solid pressure we obtained earlier with P, which is the unfactored load, actual load that is acting upon the column, which is 1000 plus 700, and the A. Since this is actually a square foot, we are asked to design a square isolated footing, so the dimensions are equal for each side. So B. So yeah, it's B squared. So basically, we are going to write the formula as 169.1 equals, 169.1 equals 1000 plus 700. It is unfactored, okay? So yeah. And over B squared, we can get the value of B as 3.17 millimeters. Yeah, that's it. So the next step is to, wait, let me get a new paper. The next step is to get the use the factored loads this time to get the Q ultimate and P ultimate for the punching and wide beam shear, for checking those things. Okay, so yeah, use factored load. So we can say PU is equal to 1.2 of the dead load, which is 700, plus 1.6 of the live load, which is 1000. We can get the value of 2440 kilonewtons for our P ultimate. So yeah, for the Q ultimate, we can get the value of, we just need to use the PU over the area of the whole, by the area of the whole footing. So we just need to square what we got earlier, which was 3.17. So yeah, 2440 kilonewtons all over 3.17 meters. QU now is equal to 242.81 kilopascals. The next part, which is the checking for the wide beam shear and the punching shear, will be discussed by my group mates later. So yeah.
The next part is to find the effective depth using punching shear. Recall that RQU is equals to P over A, which is equals to 2,440 kilonewton, which was solved a while ago, over 3.17 squared, which will give us the value of 242.81 kilonewton. After that, take note that our FC prime is equals to 21 MPa and our Fy is equals to 360 MPa. We know that our shear ultimate is equals to VU is equals to 0.75 safety factor times VC times VW times the effective depth. This is 0.75. VU is equals to 2,400 kilonewton, our factored load, minus 242.81, which is our QU, times 0.6 plus D squared. 0.6 D squared came from this 600 plus D times the squared. Then our VC is the shear of concrete is equals to 1/3 square root of 21. The unit is MPa. Remember that our safety factor is equal to 0.75. Substitute the values to our equation. We have 2,440 kilonewton minus 242.81 times 0.6 plus the effective depth squared plus is equals to 0.75 times 1/3 square root of 21 times B, which is 0.6 plus D times 4 times D, which came from this part, 600 plus D times the side times the effective depth times the conversion factor, which is 1000 squared over 1000. We can now find our effective depth, which is 0.4509 meter, or D is equals to 0.451 meter.
Okay, to check the wide beam shear, we will have a strip here, and the distance from the center of the footing is the 1.585 minus 0.3 minus D. Here, this is the strip we need, and this will be the dimensions that it will have. It will have a it will be by 3.17 by 1.285 minus D by D. And to check the wide beam shear, we will need to find the D by using this formula. VU is equal to phi Vn. And to find the VU, we will need QU, which is 242.81, and times to the area of its action, which is 242.81, 1.285. The area is the base. It is where the soil pressure acts, which is equal to the phi, which is 0.75, and VC, which is square root of FC prime. FC prime is given as 21 over 6, and the area where this acts, which is the shear, the cut, which is given as 3.17 times D, and we have a 1,000 for it to become a meter, since this will result to millimeter. And the computed result will be D is equal to 0.382 meters. Okay.
Good afternoon, this is Jesse Golveo and I talk about steel reinforcement computation. To steel reinforcement computation, we need the maximum moment. The maximum moment can be solved by the soil pressure times the base times the distance from the edge of the column to the edge of the footing. It is 1.285 meters times its midpoint, 1.285 over 2. So the maximum moment has a value of 635.48 kilonewton meter. By the way, the given FC prime is equal to 28 megapascal and Fy steel is 360 megapascal. So from equation mu is equal to phi ru bd squared, we can solve for the value of ru. Substituting 635.48 times 10 to the 6 times 10 to the 6 is the conversion for kilonewton to newton and meter to millimeter. So equal to rho is equal to 0.9 ru, the base is 3170 mm times 600 mm. Ru is equal to 0.62. After solving Ru, solve for the steel ratio formula. Steel ratio from the formula rho is equal to 0.85 Fc prime, which is 28 megapascal, over Fy quantity 1 minus 2 times Ru 0.62 or 0.85 times Fc prime. Rho is equal to 0.002, which is less than the rho minimum, which has a value of 0.0039. Therefore, we use rho minimum solving for area of steel. Area of steel is equal to 0.0039, or the rho minimum times the base times the depth squared, times the depth rather, 600. Area of steel is equal to 7,417 mm squared. Say we use diameter 25 mm, so number of 25 mm diameter steel bar is equal to the area over the area of 25 mm diameter steel bar, which is approximately 16 bars.
After checking the adequacy of the depth and knowing the number of flexure bars of the footing, you can already show and draw the details. In detailing the front view of the footing, how the flexure bars will be shown in the actual footing should be drawn here. Also, the diameter, clear spacing, and concrete cover of the flexure bars should be detailed. Next, the lateral ties are here. Its diameter and clear spacing are detailed also. And lastly, for the vertical bars, you should show at least the diameter of the vertical bars. Also, one important thing to be considered in detailing the footing is the dimensions. Lastly, you can see here the 150 mm thick of gravel bed.